Welcome to Somnifly. Today, we're taking off on an exciting journey through the world of science. Look out the window. Where do you think we're headed this time? Take a guess and drop the name of a city in the comments below. Who knows? Your pick might just be our next destination. And while you're at it, don't forget to subscribe so you never miss a flight. Today's lecture is all about the sun, our life-giving star and the engine of the solar system. Buckle up, because we're about to dive into some stellar science. Let's get started. Let's take a moment to think about the sun, not just as that bright ball in the sky that warms our faces, but as a cosmic powerhouse, a living, breathing star. It's fascinating to realize that our sun is a star just like the countless others scattered across the night sky, but it feels special because it's ours. Without it, there's no life, no seasons, no blue skies. Pretty amazing, right? Now, here's the thing about the sun. It's not just sitting there idly glowing. Deep inside its core, a fiery symphony of nuclear reactions is constantly playing out. At its heart, the sun is a massive fusion reactor. This is where hydrogen, the simplest element in the universe, gets transformed into helium. Think of it like this. Every second, the sun takes 4 hydrogen atoms, smashes them together, and voila, you get 1 helium atom. But that's not all. During this process, a tiny bit of the original mass vanishes, and that missing mass gets converted into energy. This is Einstein's famous equation in action: mass turning into energy. This energy comes out in different forms. Some of it is carried away by particles called neutrinos. These neutrinos are pretty cool because they're almost like ghosts. They hardly interact with anything. They zip right through the sun and out into space, even through our planet. By studying neutrinos, scientists can peek directly into the sun's core, like opening a window to see what's going on inside. It's like having an X-ray vision into the heart of a star. Now, the rest of the energy, the part that really matters to us, gets released as light and heat. These photons, or particles of light, start their journey from the sun's core. But it's not a straight shot. It's more like a bumper car ride on steroids. These photons bounce around, colliding with other particles, getting absorbed and re-emitted over and over. It can take thousands, even millions of years for a single photon to make its way from the sun's core to the surface. But once it finally escapes, it takes just over 8 minutes to travel the 93 million miles to Earth. That means the sunlight we see right now started its journey long before we were even thinking about this conversation. What's remarkable is that this endless release of energy keeps the sun stable. You've got gravity pulling inward, trying to make the sun collapse, and then there's all this heat and pressure from nuclear reactions pushing outward. It's a perfect cosmic balancing act, keeping the sun in shape for billions of years. Right now, it's about middle-aged, around 4.5 billion years old, with roughly the same amount of time to go before it starts to evolve into something entirely different. Speaking of its future, the sun's life story is both awe-inspiring and a little bittersweet. Someday it'll run out of hydrogen in its core. When that happens, it'll puff up into a red giant, a massive bloated version of itself. Eventually, after some dramatic fireworks involving helium burning, it'll shed its outer layers and settle down as a white dwarf, a hot, dense remnant about the size of Earth. That's the destiny of our sun and the end of its role as the life giver to our planet. But let's not get too ahead of ourselves. For now, the sun is in its prime, steadily shining and sustaining life on Earth. It's a cosmic marvel, a giant nuclear engine floating in space, and it's the reason we're all here. Pretty cool, huh? The sun is like a cosmic layer cake, with each layer playing a critical role in its function as a massive, self-sustaining fusion reactor. Starting at its core, we're talking about a realm of extreme conditions, where the temperature is tens of millions of degrees and the density is over 100 times that of water. These conditions are what make nuclear fusion possible. It's here, in the sun's heart, that hydrogen atoms are squeezed together to form helium, start releasing energy in the process. This energy is what keeps the sun shining and prevents it from collapsing under its own gravity. Moving outward, we hit the radiative zone, which stretches out to about 70% of the sun's radius. The energy produced in the core makes its way through this zone, but it's no straight shot. The photons created in the core are constantly absorbed and re-emitted. zigzagging their way outward in a journey that can take hundreds of thousands of years. Imagine a light bulb trying to shine through a dense fog. Every bit of light has to fight its way through countless particles before it finally escapes. After the radiative zone, we get to the convective zone where things really start moving. In this region, the temperature drops enough that the gas becomes opaque, and radiation alone can't effectively transfer energy anymore. Instead, hot gas bubbles up to the surface in a process called convection, similar to boiling water in a pot. These movements not only transport energy outward, but also create surface phenomena like granules and, more dramatically, sunspots. Speaking of the surface, let's talk about the sun's outermost layers. The photosphere is what we see as the visible surface, even though it's not solid. This layer is incredibly thin, only a few hundred miles deep, and has temperatures ranging from about 5,000 to over 6,000 degrees. It's here that light finally escapes into space, carrying with it information about the sun's composition and activity. Above the photosphere lies the chromosphere, a thin, colorful layer that becomes visible during solar eclipses as a reddish glow. It's a dynamic zone where temperatures start to rise dramatically. And then there's the corona, the sun's outermost atmosphere, which extends for millions of miles into space. The corona is incredibly hot, millions of degrees hotter than the sun's surface. Scientists are still puzzling over why this is the case, but one idea involves powerful magnetic fields flinging energy outward. Now, here's something fascinating. The sun doesn't rotate as a solid ball. Since it's made of plasma, different parts spin at different rates. The equator completes a rotation in about 25 days, while the poles take closer to 38. This differential rotation creates all sorts of magnetic tangles, which play a big role in solar activity, like sunspots and solar flares. And let's not forget that the sun is a living, changing star. Right now, it's incredibly stable, thanks to the balance between the inward pull of gravity and the outward pressure from fusion. This stability gives us a steady source of light and heat. But over time, as the sun converts hydrogen into helium, its composition slowly changes. It's like a slow-burning fuel tank, and when the hydrogen runs out, the sun's structure will shift dramatically. What's remarkable is that even though the sun is mostly hydrogen and helium, less than 2% of its mass is made up of heavier elements like oxygen, carbon, and iron. These elements settle differently throughout the sun's layers because the inner regions don't mix much with the outer ones. This means the sun's surface composition doesn't perfectly reflect what's happening deeper inside. The sun formed around 4.5 billion years ago and has been pretty steady since then. It's not going anywhere soon, but its life on the main sequence, the stable phase it's in now, has an expiration date. In about 5 billion years, it'll run out of hydrogen in its core, swell into a red giant, and eventually settle down as a white dwarf. For now, though, we're living in the golden age of our sun's existence, benefiting from its life-giving energy. Amazing to think that all this complexity and activity is happening just to give us sunny days and warm summers. Let's dive into what's really happening in the sun's core. You might already know that the sun gets its energy from nuclear fusion, but what does that actually mean? At its simplest, fusion is the process where lighter atoms, like hydrogen, smash together to form heavier atoms, like helium. But here's the catch. It's not as simple as one hydrogen atom turning into helium in a single step. Oh no, it's a multi-step process, like a cosmic assembly line, and it's happening trillions of times every second in the sun's core. The most important of these processes is called the proton-proton chain, or the pp cycle. It's the main event responsible for more than 98% of the sun's energy. Picture this. 2 protons, or hydrogen nuclei, collide. Now, protons don't naturally want to stick together because they're both positively charged and like charges repel. But in the sun's core, where the temperature is in the tens of millions of degrees and the pressure is through the roof, things get wild. Occasionally, 2 protons overcome this repulsion and fuse. One of the protons transforms into a neutron, and together they form something called deuterium, which is a heavier version of hydrogen. Here's where it gets interesting. This fusion releases energy in the form of light, heat, and tiny particles called neutrinos. Neutrinos are fascinating because they're almost ghost-like. They barely interact with anything, which means they shoot straight out of the sun and zip across the universe. In fact, right now, billions of them are passing through your body without you even noticing. And guess what? By detecting these neutrinos on Earth, we can confirm what's happening in the sun's core, like having a direct line to the action. The journey doesn't stop with deuterium. Another proton comes along and fuses with it, forming helium-3. Then, in most cases, two helium-3 nuclei collide to create a helium-4 atom, spitting out two extra protons in the process. This chain of events is where the sun gets the vast majority of its energy. But every once in a while, the helium-3 takes a different route, creating a small percentage of energy in less common reactions. These rarer processes also produce neutrinos, and they're a big reason scientists have been able to study the sun's inner workings so precisely. Now, the PP cycle isn't the only game in town. There's another process called the CNO cycle, which also fuses hydrogen into helium. But here's the twist. This cycle uses elements like carbon, nitrogen, and oxygen as catalysts. In other words, these elements help the reactions happen, but don't get consumed in the process. The CNO cycle is a bit player in our sun, contributing less than 2% of its energy. However, in larger, hotter stars, the CNO cycle takes center stage. Both cycles, PP and CNO, produce neutrinos, and that's where things get really exciting. Back in the mid-20th century, scientists started trying to detect these elusive particles. The first experiments showed fewer neutrinos than expected, leading to what was called the solar neutrino problem. For decades, researchers puzzled over this mystery. Was something wrong with our understanding of the sun, or was it the neutrinos themselves that were surprising us? Turns out, it was the neutrinos. These tiny particles can actually change their identity as they travel from the sun to Earth, a phenomenon called neutrino oscillation. Think of it like this. Neutrinos come in three flavors: electron, muon, and tau, and they can switch between these forms as they move through space. Early detectors were only sensitive to one type, electron neutrinos, so it seemed like some were missing. Once we built detectors that could catch all three flavors, the numbers lined up perfectly with predictions. The discovery of neutrino oscillations was groundbreaking. It even earned a Nobel Prize in physics. It confirmed not only that our models of the sun were accurate, but also that neutrinos have a tiny bit of mass, which was a huge revelation for particle physics. Imagine a tiny, almost invisible particle changing the way we understand both stars and the fundamental forces of the universe. So when we talk about the sun's energy, it's not just about heat and light. It's about these incredible processes that power the universe, from the fusion of hydrogen into helium to the journey of neutrinos that connect us to the heart of our star. And all of this is happening right now above our heads, keeping our planet warm and our skies bright. Let's talk about one of the sun's most fascinating quirks, its 11-year activity cycle. If you've ever seen pictures of the sun with dark spots scattered across its surface, those are sunspots, and they're key players in this cycle. Every 11 years or so, the sun goes from being relatively calm with few sunspots to an active frenzy, with sunspots popping up all over the place. And it's not just spots, the sun's entire behavior shifts. There are more solar flares, coronal mass ejections, and bursts of radiation across the electromagnetic spectrum. But why does this happen? The root of it all is the sun's magnetic field. Picture the sun as a giant ball of hot electrified plasma, where magnetic fields are constantly being stretched, twisted, and tangled by the sun's rotation and convection. These magnetic fields are what create sunspots, which are cooler, darker regions where the magnetic field lines burst through the sun's surface. During the active part of the cycle, the sun's magnetic field is at its wildest, with intense activity and frequent eruptions of energy. By the time the cycle winds down, the field has calmed and sunspots become rare. Here's the kicker. The sun's magnetic field doesn't just reset itself every 11 years. It flips. That's right, the magnetic poles switch places, so north becomes south and vice versa. This means that the full magnetic cycle actually takes about 22 years to complete. Every 11 years, we see one half of this flip marked by an uptick in solar activity. It's like clockwork, though not a perfectly accurate one. Cycles can vary by a year or two, sometimes longer, and the intensity of each cycle isn't always the same. This cycle isn't just something we've recently discovered. The first observations linking sunspots to an 11-year cycle were made in the mid-19th century by a German astronomer named Heinrich Schwab. Later, Rudolf Wolf developed a system for counting sunspots, which gave us a detailed record of solar activity stretching back to the mid-18th century. Thanks to these early observations, we now have a timeline of the sun's moods over the past few centuries. So what does an active sun look like? At the height of its cycle, you'll see sunspots clustered near the sun's equator, flares erupting with dramatic bursts of energy, and massive loops of plasma called prominences arcing out into space. The sun also pumps out more ultraviolet and X-ray radiation, which can have significant effects on Earth. During solar maxima, these bursts of energy can disrupt satellites, knock out power grids, and even mess with GPS systems. And while the sun's overall energy output doesn't change much, less than 0.1%, it's enough to slightly impact Earth's climate. One thing to note is that the sun's activity doesn't just follow this 11-year rhythm. Over longer timescales, the sun has periods of unusually high or low activity. For instance, between the mid-17th and early 18th centuries, during what's known as the Maunder minimum, sunspots nearly disappeared for about 70 years. This period coincided with the Little Ice Age, a time of cooler global temperatures. Coincidence? Maybe not. Scientists are still piecing together how solar activity influences our climate. But here's where things get tricky. Despite all our observations, we still don't fully understand why the sun has this cycle. We know it's tied to the magnetic field, but the details of how the field is generated and evolves are incredibly complex. That's why predicting the sun's behavior beyond a few years is so difficult. Right now, we can only make accurate forecasts about 2 or 3 years into a new cycle. Still, the sun gives us plenty of clues. For example, sunspots don't just randomly appear, they migrate. Early in the cycle, they show up at higher latitudes, around 30 to 40 degrees from the equator. As the cycle progresses, they drift closer to the equator. By the time the next cycle begins, the pattern starts all over again. Here's something cool to think about. The sun's magnetic field isn't just a local phenomenon. It stretches far out into space, influencing the entire solar system. During solar maxima, the sun's activity creates a kind of magnetic bubble that shields us from cosmic rays, high-energy particles from outside our solar system. But during solar minima, this protective shield weakens, allowing more cosmic rays to reach Earth's atmosphere. These particles interact with our atmosphere to produce isotopes like carbon-14 and beryllium-10, which we can measure in tree rings and ice cores to study past solar cycles. In short, the sun's 11-year cycle is a powerful reminder of just how dynamic and interconnected our star is. It's not just a glowing ball in the sky, it's an ever-changing magnetic powerhouse with rhythms and patterns that ripple through our entire solar system. And even though we don't fully understand it yet, the sun's cycle is a puzzle that keeps us looking up and asking questions. Let's zoom in on the sun's surface and explore the fascinating structures that make it so dynamic and alive. If you've ever seen those amazing images of the sun's surface with dark spots and bright loops, you've glimpsed some of its most intriguing features. These include sunspots, prominences, spicules, and faculae, not to mention the chaotic flashes of solar flares and the massive ejections of plasma. The sun is anything but a static ball of gas. The first thing to know about the sun's surface, or the photosphere, is that it's not smooth. It's made up of countless tiny cells called granules, each about the size of Texas. These granules are the visible tops of convection cells. Think of them as bubbling pots of plasma, with hot gas rising in the bright center and cooler material sinking along the darker edges. They don't last long, just a few minutes before breaking apart and being replaced by new ones. The result is a constantly shifting, dappled texture across the sun's surface. But granules aren't the only patterns we see. On a larger scale, there are supergranules, massive structures tens of thousands of miles wide. These are also driven by convection, but they're slower and last about a day. Supergranules are harder to spot directly, but their motion can be traced by looking at how gas moves in the sun's outer layers. And then there are the sunspots, arguably the most famous feature of solar activity. These dark patches can range from smaller than Earth to many times its size. They're cooler than the surrounding surface, which is why they appear darker, but they're still incredibly hot, about 5,000 degrees Fahrenheit. What makes them cool? Magnetic fields. Sunspots form where the sun's magnetic field lines twist and poke through the surface, suppressing convection and preventing hot plasma from rising. The result is a cooler, darker area. Sunspots tend to appear in pairs or groups linked by magnetic field lines, and their number fluctuates with the sun's 11-year activity cycle. During solar maxima, you'll see more spots. During minima, they're fewer and farther between. They're also more than just a pretty sight. Sunspots often mark the locations of powerful solar flares and coronal mass ejections, events that can send bursts of energy and particles hurtling toward Earth. Balancing out the dimming effect of sunspots are bright regions called faculae, often found near sunspots. Faculae are formed by concentrated magnetic fields, which create small hot regions that shine brighter than the surrounding surface. If you look at the sun's edge or limb, faculae stand out even more because of the angle of view. They help to keep the sun's overall brightness steady, even during periods of high sunspot activity. Now let's talk about the atmosphere above the photosphere, where we find some of the sun's most spectacular features. Prominences are massive, looping structures that rise above the sun's surface, supported by magnetic fields. They're made of relatively cool, dense plasma, cool by solar standards, that is, since they're still thousands of degrees hot. When viewed against the dark backdrop of space, prominences appear as glowing arches. But if one lies in front of the sun's disk, it shows up as a dark filament, like a shadow stretching across the surface. Some prominences can reach heights of hundreds of thousands of miles and last for weeks. For something more fleeting, there are spicules, short-lived jets of plasma that shoot up from the sun's surface and then collapse within minutes. They're like little fireworks, constantly popping up and fading out. Spicules are much smaller than prominences, but there are so many of them that they form a kind of forest, with thousands visible at any moment. Of course, the sun isn't just about steady features. It's also a stage for dramatic events. Solar flares are sudden bursts of energy, often tied to regions around sunspots where magnetic fields are most intense. These flares release energy across the spectrum, from X-rays to visible light, and they can accelerate particles to nearly the speed of light. When flares are accompanied by coronal mass ejections, massive eruptions of plasma and magnetic fields, they can send shockwaves through the solar system, creating auroras and sometimes disrupting satellite communications or power grids on Earth. What's fascinating is that while we've made tremendous progress in observing and understanding these solar phenomena, many mysteries remain. For instance, we're still piecing together exactly how magnetic fields generate such incredible structures and events. Competing models try to explain the details, but the sun keeps surprising us. All of this activity, the granules, the sunspots, the prominences, the flares, comes down to one thing: the sun's magnetic fields. These fields twist and tangle as the sun rotates and its plasma churns. The result is a surface and atmosphere that are constantly in motion, offering endless fascination for scientists and skywatchers alike. Let's talk about one of the most breathtaking sights in astronomy: the sun's corona. If you've ever had the chance to see a total solar eclipse, or even just a photograph of one, you've seen the corona as that glowing halo of light surrounding the darkened sun. It's hauntingly beautiful and a little mysterious, isn't it? But what exactly is it? The corona is the sun's outer atmosphere, extending millions of miles into space. It's unimaginably hot, with temperatures in the millions of degrees, yet it's also incredibly sparse, so thin, in fact, that we can't normally see it against the brightness of the sun. That's why eclipses are so special. When the moon perfectly blocks the sun's bright disk, the faint light of the corona becomes visible, revealing its complex, delicate structure. Thanks to advances in technology, we no longer have to wait for eclipses to study the corona. In the 1930s, astronomers developed an instrument called the coronagraph, which creates artificial eclipses by blocking out the sun's bright disk, letting us observe the corona at any time. And now, with satellites and space telescopes, we can study it in detail across ultraviolet and X-ray wavelengths, where the corona is brightest, without interference from Earth's atmosphere. So what makes the corona so unique? For one, its temperature. While the sun's surface is only a few thousand degrees Fahrenheit, the corona soars to millions of degrees. This extreme heat puzzled scientists for decades because it's not what you'd expect. The further you get from the sun's surface, the cooler it should be. It's like stepping away from a campfire and feeling hotter. We now think this heat comes from magnetic waves and plasma movements carrying energy up from the surface, though the exact details are still being worked out. The corona's structure is shaped by the sun's magnetic field. Plasma, the hot ionized gas that makes up the corona, moves along magnetic field lines, creating intricate patterns. During solar minima, when the sun is less active, the corona appears simpler, with most of its features clustered near the equator. But during solar maxima, it becomes more symmetrical and chaotic, with loops and arches stretching out in all directions. One of the most striking features of the corona is the coronal hole. These are darker regions where the sun's magnetic field opens up into space, allowing plasma to flow out freely. This plasma becomes the solar wind, a stream of charged particles that travels through the solar system. The solar wind is fascinating because it affects everything in its path, from creating auroras on Earth to shaping the tails of comets. It even forms a bubble around the entire solar system called the heliosphere, protecting us from some of the cosmic radiation beyond. And then there are coronal mass ejections, or CMEs, which are like the sun's fireworks. During these events, massive amounts of plasma and magnetic energy are hurled into space, sometimes at speeds of over 1 million miles per hour. These ejections are often associated with solar flares and prominences, and they can cause geomagnetic storms on Earth. When a CME slams into Earth's magnetic field, it can disrupt satellites, communications, and even power grids. But it also gives us the spectacular light shows of the northern and southern lights. Interestingly, our understanding of the corona and its behavior has been shaped not just by advanced technology, but also by centuries of eclipse observations. Even today, astronomers chase eclipses around the globe, using them to capture high-resolution images and data that ground-based coronagraphs and satellites can't quite match. And there's something poetic about that. The idea that for all our technological progress, we still rely on one of nature's most awe-inspiring events to unlock the secrets of our nearest star. So the next time you see a picture of the sun's corona or hear about a solar eclipse, remember that this shimmering halo isn't just beautiful. It's a window into the sun's most dynamic and mysterious processes. From shaping the solar wind to creating dazzling auroras, the corona is a reminder of the incredible power and complexity of our star. Imagine for a moment that the sun could sing. The vibrations wouldn't be a melody we could hear, but more like a low, constant hum with countless harmonies layered on top. These vibrations, waves rippling across and through the sun, are what we study in helioseismology, the science of decoding the sun's internal structure by observing its oscillations. It's like using sound waves to map the unseen, letting us explore the sun's hidden depths without ever leaving Earth. The sun's oscillations are caused by turbulence near its surface, where hot plasma is constantly rising, cooling, and sinking back down. This churning motion creates waves that travel inward. But here's where it gets interesting. The sun acts like a giant resonating chamber. These waves bounce around inside, reflecting off different layers and interacting with one another, creating standing waves, patterns that stay in place while the energy vibrates. Now, these waves don't just randomly jiggle the sun's surface. They follow precise rules, and their behavior depends on what's inside the sun. Some waves, called P waves or pressure waves, travel primarily through the sun's outer layers, like the convective zone. Others, known as G waves or gravity waves, probe deeper into the sun, even reaching its core. By measuring these waves, we can infer what's happening at different depths. How do we measure something as subtle as solar oscillations? The trick is watching for tiny shifts in the sun's surface using the Doppler effect. As the waves push the plasma up and down, light from the surface is slightly stretched or compressed, changing its wavelength. By analyzing these shifts, we can detect the oscillations. The first evidence of these waves was discovered in the 1960s, when astronomers noticed the sun's 5-minute oscillations, waves with a period of about 5 minutes rippling across its surface. Helioseismology isn't just about spotting these waves, it's about interpreting them. Waves that dive deep into the sun speed up as they pass through denser, hotter layers, then slow down as they return to the surface. The time it takes a wave to complete its journey tells us about the sun's interior conditions, like the temperature, density, and even the speed of sound at various depths. By piecing together data from waves traveling along different paths, we construct a detailed map of the sun's interior, layer by layer. This has led to some groundbreaking discoveries. For instance, we've pinpointed the location of the sun's tachocline, a boundary between the convective zone and the radiative interior. It's about 70% of the way to the sun's surface and is thought to play a key role in generating the sun's magnetic field. We've also learned about the sun's rotation. Unlike a solid object, the sun's outer layers rotate at different speeds depending on latitude and depth. Helioseismology has helped us map these rotation patterns, revealing that the sun's equator spins faster than its poles. But helioseismology doesn't just explore the big picture. Local helioseismology focuses on smaller, more specific features, like sunspots. When waves encounter a sunspot, their behavior changes. They slow down, scatter, or even get absorbed. By studying these interactions, we can probe beneath the surface of a sunspot, uncovering details about its structure and the magnetic forces at play. This technique also lets us investigate large-scale flows beneath the surface, such as the plasma currents that help drive the sun's activity cycle. Interestingly, the study of solar oscillations has even helped solve the famous solar neutrino problem. For years, scientists noticed a puzzling discrepancy. The number of neutrinos detected from the sun was much lower than expected. Helioseismology confirmed that our models of the sun's structure were correct, suggesting the problem lay with the neutrinos themselves. Later discoveries showed that neutrinos could change types as they traveled, resolving the mystery and reshaping our understanding of particle physics. Of course, we don't rely solely on ground-based telescopes for this kind of research. Space missions like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, have revolutionized helioseismology. By observing the sun continuously from space, these missions provide the high-precision data we need to track oscillations and refine our models. Helioseismology has even inspired a new field, astroseismology, where we study the oscillations of other stars. By applying similar techniques, scientists can uncover details about distant stars' internal structures, ages, and evolution. It's like helioseismology has given us the keys to unlock the secrets of not just our sun, but the entire universe of stars. So, the next time you see the sun, remember that it's not just a glowing ball of gas. It's alive with vibrations, humming with the secrets of its inner workings. Helioseismology is like listening to the heartbeat of our star, a rhythm that tells us where we come from and connects us to the cosmos. Let's talk about one of the sun's most dramatic and powerful phenomena, solar flares. These are like colossal bursts of energy, explosions so intense that they can outshine the entire sun for brief moments. They're also the source of some of the biggest disruptions in our modern world, capable of knocking out satellites, disrupting communications, and even causing power grid failures. But before we dive into why they're so impactful, let's figure out what they are and how they happen. A solar flare is essentially the sun releasing an enormous amount of energy all at once. It happens when the sun's magnetic field lines, those invisible pathways that guide plasma, get tangled and suddenly snap into a new arrangement. This process, called magnetic reconnection, releases a burst of energy in the form of light, heat, and fast-moving particles. These flares typically occur in areas where the sun's magnetic fields are strongest, like around sunspots. The first recorded observation of a solar flare happened in 1859, during what's known as the Carrington event. On September 1st of that year, an amateur astronomer named Richard Carrington noticed a sudden flash of light on the sun while observing a group of sunspots. Hours later, Earth experienced one of the most intense geomagnetic storms ever recorded. Auroras lit up skies as far south as Cuba, and telegraph systems worldwide malfunctioned. Some even caught fire. That flare is still considered the strongest we've ever documented. Flares like the Carrington event are rare, but even smaller ones can pack a punch. Flares are classified by their intensity, using a system that starts with the weakest, A, and progresses through B, C, M, and the strongest, X. Within each category, numbers indicate increasing intensity. For example, an M5 flare is 10 times stronger than an M1, and an X10 flare is 10 times stronger than an X1. The Carrington event, scientists estimate it was around X40, enormous by any measure. Flares don't act alone either. Many of them are accompanied by coronal mass ejections, or CMEs. While flares release energy as light and radiation, CMEs launch billions of tons of plasma and magnetic fields into space. When a CME is directed toward Earth, it can create geomagnetic storms that affect satellites, power grids, and even astronauts aboard space stations. In 1989, for instance, a strong solar flare and CMEME caused a blackout in Quebec, Canada, leaving millions without power for hours. But why do we care so much about these events? One reason is their effect on technology. Modern society relies on a vast network of satellites for communication, navigation, and observation. When solar flares release bursts of X-rays and ultraviolet light, they can ionize Earth's upper atmosphere, disrupting radio signals and GPS systems. CMEs, on the other hand, can induce electric currents in power lines and pipelines, causing equipment to overheat or fail. Spacecraft are especially vulnerable because they're directly exposed to the sun's energetic particles. Solar flares also have a more subtle impact on Earth's atmosphere. During periods of intense solar activity, the sun emits extra ultraviolet and X-ray radiation, which heats and expands Earth's upper atmosphere. This increased drag can cause satellites in low Earth orbit to slow down and eventually re-enter the atmosphere unless their orbits are adjusted. Even astronauts aren't immune to the effects of solar flares. Outside Earth's protective magnetic field, the high-energy particles released during a flare can pose serious health risks. Future missions to the Moon or Mars will need to plan for this, possibly by including shielded areas in spacecraft where astronauts can take cover during periods of heightened solar activity. It's not just humans who feel the sun's wrath. Solar flares and CMEs also shape the cosmic environment. They drive the solar wind, create shockwaves in the heliosphere, and influence space weather throughout the solar system. They're even responsible for some of the most beautiful natural phenomena on Earth, auroras. When charged particles from the sun collide with Earth's magnetic field, they create glowing curtains of light in the polar skies. The good news is that we're getting better at predicting solar activity. Observatories like NASA's Solar Dynamics Observatory and NOAA's Space Weather Prediction Center monitor the sun around the clock, watching for signs of flares and CMEs. They give us advance warnings so we can take steps to protect satellites, power grids, and astronauts. But predicting the exact timing and intensity of these events is still a challenge. One of the biggest open questions is whether the sun could produce a flare even stronger than the Carrington event. Observations of other stars suggest it's possible. Similar stars occasionally release superflares, hundreds of times more powerful than anything we've seen from our sun. These events are incredibly rare, but if one were to happen, it could have catastrophic effects on our technology. Fortunately, the sun's current state of activity makes such superflares unlikely, at least for now. Solar flares remind us of the sun's immense power. They're a dramatic demonstration of how something happening 93 million miles away can affect us so profoundly. And while they can pose risks, they also give us a front row seat to some of the most incredible energy releases in the universe. Whether you're marveling at an aurora or watching data streams from solar observatories, it's hard not to be in awe of the dynamic, fiery star that makes life on Earth possible. The sun is an incredible star, stable, reliable, and the cornerstone of life on Earth. But like all stars, it has a story, one that began billions of years ago and will continue long after Earth is gone. What's fascinating is how the sun's evolution has shaped and will continue to shape the conditions for life on our planet. Right now, the sun is in the prime of its life. It's stable because of a delicate balance. Gravity pulling inward is perfectly matched by the pressure created by energy from nuclear fusion in its core. This fusion is what keeps the sun shining as hydrogen atoms combine to form helium, releasing immense amounts of energy. If the sun's energy production ever increased, it would expand slightly, cooling and stabilizing itself. If it decreased, the sun would contract, raising its core temperature and reigniting the reactions. This self-regulating cycle keeps the sun's energy output remarkably steady. Even so, the sun's energy isn't transmitted instantly. It takes tens of thousands of years for energy created in the core to reach the surface, which adds to the sun's stability. If fusion in the core stopped suddenly, which don't worry it won't, we wouldn't notice any change on the surface for thousands of years. And even if fusion halted entirely, the sun could continue shining for millions of years by slowly contracting, releasing gravitational energy. This is why the sun is such a dependable source of light and heat over long timescales. The sun's lifespan is about 12 billion years, and it's currently about halfway through its life as a main sequence star. During this phase, the sun steadily converts hydrogen into helium, and its brightness gradually increases. In fact, the sun was about 30% dimmer when Earth first formed 4.5 billion years ago. This dimmer sun presents a puzzle known as the faint young sun paradox. If the sun's output was so much weaker, why wasn't Earth a frozen wasteland? Geological evidence shows that liquid water existed on Earth's surface billions of years ago, which suggests a warmer climate. Scientists believe greenhouse gases like carbon dioxide and methane may have trapped enough heat to compensate for the sun's lower energy, but the exact solution to this paradox remains an active area of research. Young sun wasn't just dimmer, it was also more active. It rotated faster, which meant stronger magnetic fields, more intense solar winds, and frequent powerful flares. This activity shaped the atmospheres of the planets in the solar system. Venus likely lost its water due to this intense radiation, and Mars's thin atmosphere may have been stripped away over time. Earth was shielded by its magnetic field, but the sun's high-energy ultraviolet light still had a significant impact, breaking apart molecules in the atmosphere and altering its composition. As the sun ages, its brightness will continue to increase, with profound consequences for Earth. In about 1 billion years, the sun's luminosity will rise by about 10%. That might not sound like much, but it will cause Earth's oceans to evaporate, triggering a runaway greenhouse effect similar to what happened on Venus. The surface will become unbearably hot, and even the deepest life forms will perish. By the time the sun leaves the main sequence, in about 5 billion years, Earth will have been uninhabitable for a long time. When the sun runs out of hydrogen fuel in its core, it will expand into a red giant, swallowing the inner planets and possibly Earth. During this phase, its outer layers will puff out, and its core will begin fusing helium into heavier elements like carbon and oxygen. Eventually, the sun will shed its outer layers entirely, creating a beautiful planetary nebula, and what's left of the sun will shrink into a white dwarf, a dense, hot remnant about the size of Earth. This white dwarf will cool and fade over billions of years, marking the quiet end of the sun's life. What's remarkable is how the sun's evolution has always been tied to the story of Earth. Its steady light allowed life to emerge and thrive, while its gradual brightening has shaped our planet's climate and environment. Even in its distant future, as it expands into a red giant, the sun will change the conditions of habitability in the solar system. For example, objects in the Kuiper Belt, far beyond Pluto, might briefly find themselves in the sun's habitable zone. It's a fascinating reminder that while our planet's time is limited, the sun's influence will persist across the solar system. The sun's journey is a story of balance, transformation, and inevitable change. It's a reminder of our place in the cosmos, bound to a star that, like all stars, has a beginning, a middle, and an end. And even though we're just a small part of its timeline, the sun has shaped everything we know and will continue to inspire us to look up, wonder, and explore. And before we finish, here's a fun fact. This video was rendered in 1080p. Why? Because I'm working on a $200 laptop. Yeah, that's the level we're at here. If you want to help me step things up, the links are down below. Thanks for watching, and see you in 4K.